In this video, we are going to continue the optical properties of the nanomaterial. So, now in this slide we are going to see the size effect of the optical properties. Normally, the bulk material samples are absorbed electromagnetism, magnetic radiation. Normally, it is a visible region. Says thin films of metal may partially transmit. A small size of the metal may normally transmit just because of that insufficient material to absorb the radiation. So, example, the gold. Okay, gold films have a few thinness of nanometer thickness become a partially transparent only. Apart from insufficient material effects, there are important phenomena which come into the play in the nanomaterial. This includes dominance of the surface plasmons, quantum confinement effects, etc. Example in semiconductor quantum dots, optical absorption and emission shift to the blue, that means high energies. We already saw that what type of color will be given as a what type of color given by which material as the size of the dots decreases. The size reduction is the more predominant in this case. That is a very important point in the semiconductor. We already saw the previous unit itself as compared to metals. Okay, that is that quantum size confinement effects become more important in metals as well as at smaller size than semiconductor crystals. Okay, then here semiconductor nanoparticles on decreasing the size of the electron gets confined to the particles, defining the state the particles. Confinement effects leading to increase in the band gap energy. Here you can see this, that is a nanoparticle having the better band gap energy as compared to a cluster as well as the atom. Okay, when you are increasing the size, when you are decreasing the size, the energy will be increasing. So atom having the better energy as compared to the cluster nanoparticle. But energy gap, here you can see this, for the bulk material you can see this, the gap between the conduction and the valence band is you are getting the small energy gap. So band levels get quantized, discreted. Surface states which lie in the band gap become important, alter the optical property, change the optical properties of nano crystals. The energy level spacing increases with the decreasing the dimension. Here you see nanoparticles having the less energy size are nearly equal to the cluster, but when you are decreasing the size of the particle or the particular object, what will happen? The energy level will be increasing. Okay, next. Here you can see this, the EG, the formula, the energy effective is, you are getting the formula like that. The effective band gap of the particle of the radius r, based on that only you are getting the energy. Energy gap. Energy EG effective is effective band gap energy of the particle with the radius r. The remaining things formula is explaining. Then the the radius will be decreasing, the energy gap will be increasing. Then gallium arsenide nanocrystalline thin film deposited in the ITO substrate. Here you can see this, for the bulk gallium arsenide. Shows the wavelength. When you are decreasing the wavelength, the absorptions will be increasing. When you are increasing the wavelength, the absorption will be decreasing. Even though for the nano gallium arsenide showing the better absorption, at 500 to 600, but beyond that it will be reducing. With reducing the size of particle, the density of states become more quantized and the band gap shifts to higher energy. higher energy. Here you can see this, the absorption will be decreasing the size. Okay, absorption will be decreasing the size. When you are decreasing the size, the absorption will be decreasing. When you are increasing the size, okay, when you are increasing the size, the absorption also increasing. At the same time, the wavelength, okay, wavelength also increasing. Okay, blue shifts in absorption will be peak. Okay, absorption. Then semiconductor properties of core cell nanostructure semiconductor. The luminescent properties are the characteristics of the core. The cell leads to an enhancement of the luminescent properties of the core. Luminescence of particles are well defined with narrow spectral ranges, which depends on the particle size. Then the deposition of the semiconductor with a large band gap than that of the core. So typically result in illumination enhanced due to the subscription of radiationless recombination of mediated by the surface states. Here it will showing the cadmium selenium nanoparticle. When you are decreasing the particle, that it will be getting that the color variation. When you are increasing the size, it will be the change in the color. Okay, then the intensity also, okay, intensity also varying depending upon the size also, depending upon the size. Color of the metallic nanoparticle. Gold nanoparticle were used as a pigment of ruby colored stained glass dating back to the 17th century. We already said this because based on this only the many examples only they were given. 1 to 10 nanometer size particles gave rise to this color. Okay, thin film of gold will transmit blue violet light. Thin film of gold. Okay, here this one is cadmium. The color of metallic nanoparticle depends on the size of the nanoscale region. Bulk AU is gold and yellow color. Okay, yeah, we already saw that. Is normally bulk will be yellow color. Nanoparticles of gold have red, purple, and or blue color also. The color depends upon the size of the particle and the dielectric properties also of the medium also. Surface plasmas are excited by incident electromagnetic radiation. Okay, here you can see this. They will explain with help of the graph.